So hey, welcome everyone to the day 1 lecture of 2 questions of physics per day series. So here we are going to solve 2 questions and it will help us to establish the solid foundation of physics for the purpose of UPSC Civil Services examination. So the first question is, at a given temperature lambda max 6500 angstrom for a black body cavity, what will be the lambda max if the temperature of the cavity wall is increased so that rate of emission of a spectral radiation is doubled? Okay, so the condition is that you have to double the rate of emission of a spectral radiation. Okay, for one given temperature the lambda max is 6500 angstrom. Okay, and you have to calculate that if the spectral emission has to be doubled, then what will be the temperature. To solve this question we need two law. The first one is Stephen Boltzmann law and the second one is Wien's displacement law. So Stephen Boltzmann law says that rate of emission of a spectral radiation is fourth to the power of temperature, and Wien's displacement law says that lambda max t is a constant where b is called as Wien's constant. So we are assuming that black body is ideal, that is whatever is being observed is being emitted. So let the initial temperature be T1 and the corresponding peak wavelength be lambda 1, which is 6500 angstrom. Then as per the question the power emission doubles, so we are using the Stephen Boltzmann law. So as per the question E2 is double of E1, that means E2 by E1 is 2, and for E2 we could write sigma T to the power 4, and for E1 we could write sigma T1 to the power 4 is equal to 2, and here we have got the ratio which is T2 by T1 is equal to 2 to the power 1 by 4. Now we have given temperature and some lambda max, so we know that this is connected by Wien's law. So we could write that lambda 1 T1 is equal to lambda 2 T2. We have the lambda 1 at 6500 angstrom, and we have the ratio of T1 and T2, so we could obviously get the lambda 2. So by using the mathematical manipulation you will get the answer to be 5468 angstrom. Now let us move to the second question. So the question says that a potassium plate is placed 1 meter from a fuel light source whose power is 1 watt and it is obviously 1 joule per second. Assume that an ejected photoelectron may collect its energy from a circular area of plate whose radius r is say 1 atomic radius. So this is the case is very simple. Suppose we have sun, we have a very big sun, and from here around 15 million kilometer, okay, we have earth. So sun will throw out a lot of energy in all direction, but we cannot calculate or accumulate all the energy. Okay, we could only accumulate depending on our surface area. So the same condition is here in the case of this particular setup as well, that you have this potassium plate and you have this very feeble source of light, and very feeble source of light is traveling in the direction of potassium plate which is kept 1 meter away. So area which is collecting the energy is actually made up of the area by of 1 atomic radius. Okay, so it is around 10 to the power minus 10 meter. So the energy required to remove an electron through the potassium surface is about 2.1 electron volt. So in our definition it is nothing but a work function. So it says that suppose you have to remove 1 electron, then you have to spend 2.1 electron volt. Okay, so 1 electron volt is nothing but 1.6 multiplied by 10 to the power minus 19 joule. Okay, and the question asks that how long would it take for such a target to absorb this much energy from the light source. So the light source is sending 1 joule per second. In 1 second it is sending 1 joule energy. Then the question is that 1 joule or whatever the share that atom or of the potassium plate is going to take, what will be the time taken. So let me tell you very clearly, if the energy of the incident photons, or radiation is more than work function, then the photoelectric emission is instantaneous. This is what we have observed. Although classically it should take time, it should take time to accumulate the energy, but it happens instantaneously. This is for what Einstein got the Nobel Prize. He explained that it happens instantaneously, contrary to the classical physics belief that it should take accumulation time. So this physics is a kind of question from a very big past, great past, where we have no knowledge to explain the photoelectric effect. Okay, so let us try to solve this in that way. So we know that light spreads spherically from the source. If suppose that if this is light source, then it will spread in all direction. Okay, so the intensity will keep decreasing. So as the distance will increase, the intensity will keep decreasing, and we could calculate intensity at distance 1 meter. So intensity is nothing but power upon area. So power is 1 watt and area is 4 pi d square. D is we are going to calculate it 1 meter away. Okay, so D is going to be 1 meter. So in that way it is 1 by 4 pi watt per meter square. Now this is the light source and this is one atom. This is the light source and this is one atom. So we know that not all the thrown light is going to be absorbed by this particular one atom. So what share of the thrown or radiated energy is going to be absorbed by that one atom? The answer is very simple. It is going to be intensity times the area of that atom. So we are next going to calculate intensity times area of that atom, which will give you the power incident on the target area. When you calculate it, it is going to be 2.5 multiplied by 10 to the power minus 21 watt. So in 1 second it is going to accumulate this much joule only. But we see that this is very less than 1 joule. In 1 second this can this can send 1 joule, and this can receive only 2.5 multiplied by 10 to the power minus 21. Okay, so the time t required to accumulate this share as per the work function energy will be given by this particular equation, where we know that power is nothing but work divided by time. So time is nothing but work by power, and this is what we have prepared, that the work is in this case is going to be given by work function. Okay, and the power is 2.5 multiplied by 10 to the power minus 21. So when you divide it, you get approximately 36 seconds. So this is what we call classical result. This is what we call classical result. But in real this doesn't happen. In real the ejection happens instantaneously if the minimum threshold frequency condition is met. Okay, and we know that minimum threshold frequency is characteristic of metal and not the light itself. So physical significance goes as follow. This classical calculation predicts that photoelectron emission should be delayed by over 2 minutes. Okay, even for the relatively intense illumination, and this is the classical way of the interpretation. However, experiments show that photoelectrons are emitted instantaneously within 10 to the power minus 9 second, which is a very small time, upon illumination regardless of the light's intensity, provided that there should be minimum energy corresponding to work function. This enormous discrepancy between the classical prediction and the experimental observation was one of the key pieces of evidence that led Einstein to propose the quantum theory by using the Planck's hypothesis as well. Okay, for which he received the Nobel Prize in 1921. The conclusion is very simple. According to the classical wave theory, the potassium target would be requiring approximately 136 seconds to absorb the sufficient energy for the photoelectron emission. The fact that photoelectrons are observed instantaneously demonstrates the quantum nature of the light and failure of the classical electromagnetic theory to explain the photoelectric effect. So let me provide you some value addition. So let me try to provide you one value addition related to the fact that we have some observations related to related to photoelectric effects. So let us study that. Mm, just give me a moment. Okay, yes. Okay, so here we have few observations when we conducted this particular experiment in real. So we have few observations that minimum frequency required to get electron ejected is called threshold frequency, and corresponding energy to this is called work function. There is a maximum value for kinetic energy, and photoelectric emission is instantaneous process. Okay, it is not the accumulation process, not the accumulation process. And photoelectric current depends upon the intensity of the radiation and not the frequency. Okay, so more intense light you throw, there will be better photoelectric current. That is why in bright sunny light, you get the solar cells working better, solar cells working better, producing more power. Okay, so we could say that only last observation could be explained by the classical physics, and the first three observations could only be explained by the quantum hypothesis. That is what Einstein did and won the Nobel Prize. So let us meet in the day 2 series of the 2 questions of physics per day.